The periodic table is the ultimate catalog of all known matter in the universe. It organizes every element into its own distinct box. Look closely inside any of these boxes, and you'll find the atomic number. It is always a clean, whole number. Hydrogen is 1, helium is 2, carbon is 6. These whole numbers make perfect logical sense. Atoms are built from discrete, indivisible building blocks, like protons and neutrons. You can't have half of a proton. Then if we look at the isolated periodic table tile for an element like copper, there is a visible anomaly. The atomic number is a solid 29, but right beneath it, the mass number is 63.6. How can a physical object made exclusively from whole building blocks weigh a fraction of a particle? To solve this structural mystery, we have to look inside the nucleus. The center of an atom, the nucleus, contains protons. This specific particle count strictly determines the atomic number, and by extension, the element's identity. This visual model shows a nucleus containing exactly 6 protons, which means it is carbon. That is an absolute law of atomic physics. Any atom with 6 protons is carbon. If you alter the proton count, you alter the element. If we drop that count to only 3 protons, it cannot be carbon anymore. It must be lithium. Because protons provide a strict whole number law of identity, they can't cause our fractional mass. The decimal has to come from another variable. That leaves the other particle residing in the nucleus, the neutron. Unlike the strict rule for protons, the number of neutrons within an element's atoms can fluctuate, and the identity of the element remains exactly the same. These two models of carbon nuclei show this. The first common form, carbon-12, contains exactly 6 protons and 6 neutrons. The second rarer form, carbon-13, maintains its carbon identity with 6 protons, but possesses 7 neutrons, increasing its mass number to 13. These varying forms are called isotopes. They are atoms of the exact same element that share the same proton count, but have different neutron counts. Because isotopes only differ in their neutron count, they react identically in chemical situations, but they possess physically different weights. This proves that a single element does not have a single, uniform mass across every atom. To ground this microscopic concept into physical reality, imagine yourself scooping up a handful of raw metallic copper. Within this physical sample, every single atom obeys the proton law. May all have 29 protons. But the sample itself is actually a mixture of 2 different stable isotopes, copper-63 and copper-65. These appear in a specific natural ratio known as their abundance. On average, 69.2% of the atoms in that handful are copper-63, while the remaining 30.8% are the heavier copper-65. Real-world elements are chaotic, proportional mixtures of different isotopes. This creates a unique challenge for chemists, representing a mixed reality with just a single number on the periodic table. The scientific solution to this problem is relative atomic mass. Instead of picking one isotope, chemists calculate a weighted average of all naturally occurring isotopes for that element. This formula for relative atomic mass shows exactly how they get there. The first step is to multiply the natural abundance percentage of each copper isotope by its specific mass. That means we multiply 69.2 by 63 and 30.8 by 65. Next, we take those two resulting figures, 4,359.6 and 2002, and add them together to find a total sum of 6,361.6. Finally, we divide that total sum by 100, representing 100% of the combined isotope abundances. This gives us a final answer of 63.616, or rounded down, 63.6. This mathematically derived decimal directly matches the mass number found on the periodic table tile, definitively solving the mystery. That means the decimal mass listed for an element does not represent the literal physical weight of any single indivisible atom. The two numbers on the periodic table measure 2 entirely different things. The atomic number represents strict, unbending subatomic laws. The mass number represents statistical averages. The periodic table is a dual representation of reality. It captures both the rigid whole number rules of atomic identity and the proportional diversity of the elements as they actually exist in nature.